Yeah, thank you. Thank you very much for the invitation here. First of all, apologies. I think some of you already heard this talk, but I promise you there are new aspects, so I hope it is still interesting to you. So this is a joint project with Louis Winter. He's a PhD student in our group, and we look at a linear regression problem where the underlying variables are functions. So there are especially also in the metrics many problems or many data sets where we have sort of functional data, like there's also maybe a nice connection to your TRR electricity price curve. So you have observe electricity prices for every hour of the day. So you have a domain, the 24 hours of the day, and you have a curve observation, so to say, of these electricity prices. Or other energy market-related variables like the electricity consumption throughout the day, or the weather forecast for the next day in terms of how much wind or solar generation is expected. So we like to understand, or we like to model a regression framework where we regress curves on curves, or on many curves, and maybe also scalar variables. And these kind of models are well developed since the last 20 years, the function linear regression, where we have a well-developed theory how to build consistent estimators for the respective slope coefficient that we might want to interpret as, say, ceteris paribus effects when, I don't know, the demand increases at a specific time, conditional on other variables. What is the effect of the price curve on the price curve? And a big problem with these function regression models for practical purposes is its infinite dimensional nature. There is an impossibility result. I will discuss also more deeply in a minute, that you are not able, so you are able to construct a consistent coefficient estimator, but you will never get weak convergence of this functional estimator to some limiting Gaussian process. So we are not able to build classical inferential tools like confidence intervals or confidence sets, t-tests that practitioners typically do when they do regression analysis. And we want to address this gap with a slightly more restrictive model setup that we believe is still very plausible, under which this is possible. And this is what this talk is about. So now, some reason the
press on the computer once.
Right. So I first talk more about the motivation I just addressed a bit. The functional factor regression is the name for our approach that I will discuss first for one functional regressor variable, but that can be easily extended to multiple regressors. I then also present, after presenting the asymptotic theory, also simulations and an application to specifically electricity price curve modeling and understanding, estimating ceteris paribus effects within these functional dependencies. Let's start with some pictures. So the electricity prices, you may observe for every day such a curve. Actually, these electricity prices are settled in a specific way. They are determined through an auction. So every day at 12 p.m., there is an auction for next day prices, where all prices for all these 24 prices are determined simultaneously in an auction. So market participants come together and have information. They have, for instance, information from the system operators. What is the expected consumption of energy for the next day? Also, they have information from weather forecast. What is the expected wind and solar generation of electricity for the next day. They also have lag information of previous electricity curve prices and many more variables maybe that are available in scalar form. So we want to regress the current electricity spot price on yesterday's electricity spot price curve, like a functional autoregression, plus additional variables like these, let's say, demand side and supply side variables. So to match all the information that is available at the time where this auction took place to determine this price curve, to understand what are exactly the variables that drive these prices, to learn more about the dynamics of such an electricity spot price curve. So electricity price curves is one example where you might apply this. Other economic examples are, for instance, bond yields, yield curves. There the domain is something different. It's the time to maturity. Like 150 means the interest rate you get if you buy today a bond that expires in 150 months. And this curve, every day, or this is monthly data, you observe such a curve. It obviously depends on the inflation. So higher inflation, maybe you can expect also higher interest rates. So there is also data from professional forecasters. They give you, from which you can construct so-called inflation expectation curve, what people think, what the inflation in 40 months is expected to be. So we might regress the left-hand side curve on the right-hand side curve to understand what these dependencies are. Other examples are, so you see here you have different choices of domains. Here we have the hours of the day. Here we have the time to maturity. You can also have cross-sectional data of individuals. Maybe that's the lifetime, the age of a person. You may observe over the lifetime a person's income and maybe happiness level or other variables. You may also consider problems from macroeconomics, where nowadays big topic is heterogeneity within macroeconomic variables. Maybe you have, or across different income levels. So poor people, for instance, have a different inflation rate than rich people. So maybe for each individual across the quantile, across the income distribution, you may address to every quantile in the income distribution a different inflation rate, and might want to learn what the dynamics of this curve is. So there are many examples, and I think the most interesting examples are when you have time-dependent curves, like in our examples. So for those who are not so familiar with functional data, the idea is that data is available as realizations of some stochastic process, like that is defined over some compact domain from A to B. And T is the sample size. So this is kind of a point evaluation of such a curve. We interpret the entire curve as an L2 valued random variable, so a random function. So each curve lives in or takes values. The random function takes values in a Hilbert space, the L2 space, with a specific L2 is the L2 norm. This notation will also frequently use for the inner product. And what we typically assume, and where the strengths are in functional data analysis, if the sample paths have some specific smoothness that we exploit. So we typically assume something like continuous sample paths. If you have continuous sample paths, then also L2 is a bit a weird space because it's actually a space of equivalence classes. But if the sample path is assumed to be continuous, then each equivalence class in this L2 space has a unique representative object, and these point evaluations are well defined. So this is one reason why we assume continuity of the sample paths to have a well-defined probabilistic framework. Sometimes we assume a bit more regularity, like Hölder or differentiable, to that helps to get uniform statements when it comes to asymptotic results. And specifically for our setup, we work with functional time series. So today's curve depends on yesterday's curve. And we say that this curve, this random function xt is weakly stationary if the point-wise expected values are time invariant. And here we have a time invariant autocovariance function, or with lag tau. Of course, if there are questions, please just interrupt me. By the way, it's 1 hour the talk, or yeah, good. All right, so this is our function regression model equation. So, for instance, yt might be today's price curve, xt might be yesterday's price curve, so functional autoregression. But for those who are not so familiar with these kind of models, you may think of it as a very big vector autoregressive process. So here you might have a very large vector valued time series. Here you have a very large vector valued regressor time series, the lag. And here you have a coefficient matrix, but it is an infinite dimensional object. So instead of a coefficient matrix, you have a coefficient kernel and you integrate over it. This is how you can interpret it. We assume a classical exogeneity condition in a regression model. And this beta, so like the VAR matrix, we have here the VAR or functional AR coefficient surface. This is a result of an estimation where, so you read it like this. This is the R and this is the S. So you might, and here you see the heat map. So for instance, what happened, so it tells you something like, if yesterday's 5 a.m. prices are high, we on average have today's 5 a.m. prices also high. And it tells us also if yesterday's 7 a.m. prices are high, we can expect today's 5 a.m. prices to be low, because this is blue. This is red. So you can also make combined citrus paribus arguments in such a heat map. This is, I will be more specific about the estimator. This is, it's well known how to get consistent estimator of such a coefficient surface. The big problem that I already addressed in the introduction is we cannot, without further restrictions, test whether this is significantly different from zero, this is significantly different from zero. So instead of only this point estimate as a surface, we only also want to have something like confidence bands or t-tests. So ideally, and this is already a result from our application, ideally we want to have something like this, that we have confidence bands around this this estimated slope surface, and that under and kind of a Gaussian weak limit from which we can build pointwise. This pointwise, you can also do it uniformly. Pointwise t tests. So here, for instance, we see this p-value heat map that the 5 a.m. effect on 5 a.m. today is significantly different from zero, but the 7 a.m. negative 7 a.m. on 5 a.m. effect is not significantly different from zero. This is something we can then learn from such a p-value heat map. So And in this paper we discuss. Yeah.
What does the yellow mean?
All right. So I think so. First, these lines here. This is the 1%. So here, this is highly significant. I think the yellow was the part where we have here exactly a coefficient where between negative and positive, where the sign changes. So to say, here it was a positive coefficient, here it was a negative coefficient. But you have to read it together with that heat map. Yeah. So here it's also interesting. Here you have a night on night effect. You have here day on day effect, but across day and night there is not much happening, or maybe negative, but maybe insignificant effects. So also here you see the nighttime. Here these points are the bounds of the typical work day. Right. All right. So let us have a look at the underlying problem. So here you see the regression curve. YT regress on XT, and X. Let's look at XT. It is a function living in the L2 space. It is an infinite dimensional object, so we can represent this guy in terms of a basis. Let's pick any basis of L2. It can be a Fourier basis or basis of functional principal components, or many different choices. There is not an obvious choice like these unit vectors in a finite dimensional vector space, but pick any basis, and then you have coefficients to represent X, and there are infinitely many of them. So now, when looking at this equation, let's fix one R on the left side and fix one R, and we want to look now at XT of S and beta R of S. So we can interpret the beta of S for fixed R also as being an element in L2. So we can represent beta R of S by using the same basis expansion, using the same basis. So now let's insert the XT and beta in here. What happens is here we have an integral, here we have a basis function, so we integrate over S. Here's the S, here's the S. This basis, if it's also normal, it drops out. So it's 0 if J is not equal to L, and 1 if J is L. So we have one sum here. We have these Bj coefficients, and these Xj, these are random variables. And if we have fixed the basis, we can compute these Xj's. And what we get is a regression equation where we regress YT on these Xj's. And there are infinitely many of them. So it's a regression problem where we regress on infinitely many regressors.
R is just 1 hour of the day, or
yeah, pick one point on the domain. So let's assume that we have really a smooth observations throughout the day. In German energy markets, you have only for each hour an observation, but maybe in other, I heard in Australia or something, that we have a finer grid of. So it depends. So R is an hour of the day. Yes.
Okay, but in general, it would be a point in this continuous time domain.
Exactly. Yes. So it's any point. So on the left-hand side, you have a curve, but we make a regression for a fixed point on that left-hand side. So you can think of, you fix a point here, like the 10 a.m. price, and you estimate the slice, so to say. Yes. And if everything is sufficiently smooth, the beta will also be smooth in the end, because what happens at 10 and at 11 a.m. is very similar in the smoothness. All right, so we have this regression of YT on infinitely many X variables. If we would estimate the corresponding coefficient, we can insert them back here to get the estimate for beta, the target that we are interested in. A convenient basis is the basis of functional principal components. This is the basis if you compute the eigen functions of the covariance function or the corresponding integral operator. If we sort the eigenvalues in decreasing order, then and compute the corresponding eigenfunctions and pick also normal ones, then this gives the basis of the 2 space, or at least of the space where the subspace where xt lives in. And yeah, these in this case, these scores, these xjt, they are uncorrelated for different indices j. So to identify what the coefficient beta j is, it is just a simple regression of yt onto the corresponding xjt, because it's uncorrelated with the other. So this is how we can identify the bj of R. And given that representation, we can insert it back in here. We have a representation of beta Rs. So now this guy can be easily, consistently, with parametric rates estimated. This is not a problem under very weak assumptions. A problem is if we insert all these estimates in here and sum up infinitely many of them, we get things get more complicated. So actually, a conventional estimator is to do exactly this. We estimate the sample, where we compute the sample covariance function and compute the eigenfunctions of it. So the functions that satisfy the eigenequation with the corresponding eigenvalues. So the sample covariance is simply this guy. And we get the phi j's, the sample function principal components. And what we do is we take this representation, we truncate it, we take the estimated phi j's, and we estimate the beta j's through this relation. And to get a consistent estimator, we have to truncate it with a certain rate. So, so when do we get consistency? We need some standard regularity. I mean by that, we need weak dependence, maybe either IID or alpha mixing or something like that. And we need enough moments. So nothing complicated. And LT must tend to infinity at a rate depending on capital T. And if you take this estimator, so each bj can be estimated simply like this. We insert it in here. And if we want now to compute the difference of this guy to the true beta and multiply it by some scalar normalization, which is then supposed to be the convergence rate. If we work out the asymptotics of this guy, taking the expectation of the square, so in the mean squared sense, a term like this pops up. This pops up when you work out the asymptotics. And so it's an interplay between, here you have t, here you have the rate in front, and here you have a sum over of 1 over the eigenvalues. So suppose the function lives in a finite dimensional subspace. So there are only finitely many eigenvalues. And in this case, this guy is bounded. And you get actually, AT can be very close to square root t in this case. But in, under an infinite dimensional object, these summons, there are infinitely many of them. And the problem is, you can pick, of course, a rate LT and AT that satisfies this condition, then you get consistency. But when it comes to weak convergence, that you want a big OP here with a possible limiting Gaussian, with a Gaussian limit. So if if we have a condition that this is greater to 0, then this object cannot be tied in L2. So the problem is actually that these summons, whatever finite dimensional approximation you pick, the remaining summons will blow up in the end. So there is no possible normalization factor to make this object tied in L2. If this condition holds. But if it's equal to 0, it converges to 0. So we get consistency, but not we do not get a limiting distribution. That's a result by Mars 2007. There are also some other papers that discuss it. So without any specific additional conditions, it is not possible to get the CLT from which we can build inferential methods. Restrictive assumption that is sometimes done in practice or in more empirical related papers is to assume that xt lives in a finite dimensional space. Then everything is nice because this term is just bounded. So it is not a problem asymptotically, and you get a CLT, you get a Gaussian limit with square materials.
This has no limiting random variable, not a Gaussian one. So
it has no limiting random variable.
So, yes. I mean, there are non-standard limiting distributions in like unit root contexts, like Dickey-Fuller. This says you can also not get that.
Well, I mean, yeah, exactly. So you have, if you pick a finite number of points on the curves, then and construct a vector of it, it will give you a Gaussian limit. But together it is not tied, so you can not get a joint Gaussian limit. So the limit is in some sense Gaussian for finite dimensional approximations. So it is in the class of Gaussian limiting processes. It's nothing weird like not like Dickey-Fuller distributions, but it's just not possible due to the infinite nature. The problem is here the eigenvalues they get smaller and smaller, and so whatever you truncate, the variation that is left, there is still some variation left if you sum it up. So so I will not go into the proof details, but this 1 over kappa appears there, and you see it's a problem when it is here in the denominator. So it is not possible without further restrictions to get a limit. That this is not an infinite sum, but it's a finite sum. So there is some finite dimensional space where the curve actually lives in. Then we have this representation that if we insert this finite sum in here we get also a finite sum, and we can regress yt on these guys. So that is, of course, a solution, but it has some problems. So first, what is this L-dimensional subspace? Maybe a bigger problem I see is typically, so if you have your curve living in a finite dimensional subspace, typically observations you have, there might be measurement errors, or there might be some noisy deviations from the actual from the curve living in that finite dimensional space. And as soon as you add some noise to that representation, you leave that finite dimensional subspace. And I would say just because data contains also some noise, finite dimensional assumption is not plausible. So also another problem is L might still be large, so it might be still larger than the number of observations. So you still need some regularization. What basis functions do we choose? Of course, sample function principal components are an obvious choice, but these functional principal components are actually the components in which a function has the highest variation. What we are interested in is we will want to regress another variable onto that function. So the function principal components do not give us the directions in which the covariance with that other function is high. And especially, suppose here is a measurement error, and that is a high variation. Maybe that dominates already the variance of that term, although that guy is not relevant. So we also want to focus on the fact that actually the covariance with y is what we have. All right, large motivation. So now let's come to
one question.
yes.
Do you have any other special cases where you can have a limiting distribution than the one with the finite dimensionals special case? Is there anything else where you can get a distribution?
I guess so with different estimates. So I know if you do ridge regression, for instance, you also cannot have it. I haven't thought so these are the main dominating cases. I actually so I don't know. Maybe that so whether there is any estimator for which this is possible, I don't know. But at least for ridge regression and for function principal compounds regression, it is not possible. And it is possible if you impose restrictions on the underlying DGP, like finite dimensionality.
But other restrictions than this?
The one I propose. So what I propose is actually to add a noise term to this equation, to this finite dimensional equation. But this noise term has to satisfy a certain assumption, namely that it is not relevant, so to say, for the regression relationship with y. So what we assume is that this is our regression equation. And we assume that the regressor has two components, a finite dimensional component, like in here, and an additional, possibly infinite dimensional component that is this finite dimensional component. So xt is, by this representation, there is no specific restriction because it's still an infinite dimensional object living in L2. The restriction comes here. We assume that this additional infinite dimensional component is non-predictive for y. So we assume that this guy is actually, you might also say, independent of all other variables. We make it a bit weaker, so it's uncorrelated with y, with u, and with x star. So you can think of it as a measurement error, an infinite dimensional measurement error, or additional information that is not relevant for y. Maybe x and y are independent. There is the regression equation is 0, then x star would be 0, or the entire curve is hidden in epsilon t. So this is a much more general framework, and I would say also a more plausible framework than the one with under finite dimensionality.
Typically, measurement errors cause problems. Here they are the solution.
Okay. Yeah, okay. Maybe the saying measurement error is not the best way when it comes to heterogeneity problems. So maybe you can think of it, it's additional information in the curve. Or when it comes to, for instance, price curves, there is no measurement error. That's the outcome of the auction. It's just but maybe there are components in that price curve of yesterday that are not relevant for predicting today's price curve. Maybe only a subset of that components is relevant for. So if that is yesterday's price curve, that is today's price curve, there is a component in the yesterday's price curve, a finite dimensional component that is relevant for, say, explaining the regression relationship, explaining the conditional expectation of y given x, and the additional component is not relevant. But I agree, maybe measurement error is not the best way to motivate it.
So maybe I mean, it's not really an instrumental variable either, but it has some elements of this that on its own epsilon doesn't affect y, which is what we would also like to see from an instrument, in that it has no direct impact on y, but it sort of also so it has a connection to the regressors. So it's also not a perfect analogy, but maybe.
Yeah, right. So epsilon is related to x and it's not related to y. But here in this case, we have, this case we have a specific assumption that epsilon is also not related to x. So epsilon does not appear, if you write down the conditional expectation of y given x, epsilon does not appear in that equation. Maybe there is an analogy, but not not fully, I would say. Yes.
Do you need to also assume the same condition on the eigenvalues or the inverse of the eigenvalues of that epsilon too, that they
can be completely arbitrary? I don't need to assume any more on epsilon like this. But this equation, so to say, that comes on the next page, I can already say, it leads to a property that it lives in the null space of that beta. So assuming this leads to the fact that multiplying it with beta gives you a zero almost surely, so to say. And so it does not appear any further in the equations. The problem is, of course, to disentangling the two, identifying what they are, and estimating the x star. Because if we know the x star, then we can do a finite dimensional regression. So we assume the x star is predictive. So it's we make here x star is finite dimensional, so it has a basis representation with respect to some unknown basis, and it has some coefficients FLT, and we assume all these factors FLT they are predictive, so they have a at least not everywhere zero covariance with one. These are standard assumptions that we assume. So actually here in this paper we assume UT is a martingale difference sequence. You might also make it also time dependent, but later on we argue that we can add enough lag, so add further functional regressors as lag dependent variables that capture the dynamics. But a possible extension is to weaken that, not having not having the martingale difference sequence property. But we wanted to focus here on the simpler, well-defined, well-specified dynamics case. Process having some covariance operator. We assume alpha mixing of this joint process, and this is a condition. Beta is only identified in the subspace where xt actually lives in. That might be the full L2 space. But if there are, so to say, there is a linear combination within the domain of the x that gives you zero variance, like the multicollinearity problem, then we have to exclude that direction. That is what this condition tells us. So like the non-perfect multicollinearity condition. And we assume that we have differential sample parts. You could also do it with Hölder continuous to make it weaker, but that makes it a bit more simple. Right. So under this setup, what do we get? It does not. So we do not have yet identified all parameters, but let's insert it into our equation. So there is a what actually happens, because these epsilons are uncorrelated with all other elements. It will not. It cannot. It must live in the null space of beta. And because epsilon lives in the null space of beta, any direction psi orthogonal that is orthogonal to these directions where the finite dimensional object lives in must also live in the null space of that beta, which directly gives us a nice representation of the beta coefficient. It is a finite rank operator with unknown BLs and psi-Ls. And if we insert that in our equation, we get something like this. So we get here we get the inner product of xt with respect to that unknown directions. We can subtract the mean that we have here a different intercept. That's just a transformation. We did not impose any restrictions on the epsilon. So epsilon can also live in the subspace where x star lives in. We can assume that epsilon is also with respect to the L2 inner product orthogonal to that, but we don't do it because we actually don't need it. So that leads to a problem that the factors we write in our equation are only identified up to a noise term, and combining the two gives us this projection coefficient, what we call FLT star. So FLT star is the identifiable version of the factors FLT in our equation. And that we what we can work with. So if we know psi or have an estimate of psi mu, we can estimate also the FLT stars. So now we can regress YT on these FLT stars. We get the beta L estimates and can insert them in here, and then we have an estimate. That is the strategy. So what is now psi L? What are these psi L's, and what is the dimension? What is the dimension K? That follows by our assumptions already. So let's have a look at the cross covariance operator of xt and yt. If we insert the equation xt equal to xt star plus epsilon t into here, and epsilon t is uncorrelated with yt, it drops out, and only the factor term remains here. So this cross covariance operator has rank k. So k is the rank of that cross covariance operator. The covariance operator of our regressor is still infinite dimensional, but our model implies that the cross covariance operator of y with x that captures the directions that are relevant for our regression relationship, that is finite rank, and it's exactly the rank k. So that is the story to identify k. And now we also see that the psi's appear here on the left side. So the psi's must be linear combinations of the left singular functions of the cross covariance operator. So we might, how do we get the left singular functions? We multiply our operator with its adjoint, and then we have a symmetric operator. So we have the eigen functions of that operator, they must be linear combinations of the psi's. There is a matrix in the middle, and as always in factor models, factors and loadings are you can rotate them. So you can rotate factors and loadings by some rotation matrix. And this is an arbitrary choice, and we make it ourselves easy. We make this matrix in the middle. We rotate the factors and the loadings so that this matrix in the middle is a diagonal matrix. That is one way of normalizing it. And in this case, this product with the adjoint operator has this form. It is a nice form because you can directly read the diagonal elements must be the eigenvalues, and the psi's must be the eigenfunctions. So to estimate psi, we have to estimate eigenvalues and eigenfunctions of D, and we have to find out what is the number of these eigenfunctions. And this operator is exactly k positive eigenfunctions. And after the k, it's exactly 0. So it's like a scree plot, and it drops to 0 at some point. And we want to, this is what we want to find. So we want to estimate k. So now we have all ingredients. If we know k, we can estimate this guy, we get the psi's. And from the psi's, we can have the factors. We have these guys, and then we can estimate the b's to insert them in there. But we have to know what k is, what is the number of factors. So this is the property of the eigenvalues. The first k sample eigenvalues converge with square T rate to the true eigenvalue, the positive one. The remaining sample eigenvalues converge to 0 with the same rate. So we follow an approach by Wu to transform these sample eigenvalues so that those eigenvalues converge to 1 and those converge to 0. Then we have identified the gap. Because it's not clear where's the, looking only at the largest gap is not, there could be a larger gap within the positive eigenvalues compared to the gap from the kth one to this one here. So what we do is we find the transformation of this lambda at L so that all the positive ones converge to k and the other ones converge to 0. We also add a dummy 1 and a dummy 0 for the case that there is k is equal to 0 or k is larger than the k max we pick. the maximum one, and we pick the largest eigengap. This is our choice. We pick it from this paper by Wu, but you can also have different choices. This is a function that we just need some function. We have to apply some function to lambda L so that if I insert, so that for positive values, it converges to some positive value, and for 0 values, it stays at 0. We need it to diverge, but this divergence must be a rate lower than this rate, so we pick log t. So log t lambda hat L, because lambda hat L converges to lambda L, log t lambda hat L diverges, but log t lambda hat L for those guys, for the large, for the eigenvalues belonging to 0, the sample eigenvalues belonging to 0 eigenvalues, this still converges to 0. We have a tuning parameter in here. I will that we you have to pick. We do it via cross-validation. So we pick basically the gamma that in a rolling cross-validation, the time series setup gives us the best model fit. But from theory-wise, any positive gamma asymptotically works. So, but this is a parameter you have to choose. I think maybe you can also do a different strategy and build an information criterion that does the job. But this is our approach. So under our assumptions, the number of the largest eigengap converges to the true number of factors with probability 1. Convert the probability that it hits the true factors converges to 1 if the true kappa is within the set of kappas you look at. Probably our model is wrong, and the true k is infinity. And in this case, you will always get the kmax. So if you get kmax as a result, then this is an indication that maybe our model is not a good way to describe the true data generating process. All right, so to build everything together, we get our coefficient surface estimator like this. So we have our k estimated, we have our factors estimated using the sample analog, and we just regress. We look at the all S regression of yt on all these stacked factors here. And this was the true regression coefficient surface. So using these beta heads in here and using the psi hat Ls, we get our estimator. All right, so what are the asymptotic properties? First of all, so we want to learn what the limit of this guy is. And if you insert everything, so you want to compare this guy with this guy, there are different sources of different sources of estimation error. So first, the beta hat L has an estimation error for the beta L, the usual OLS estimation error. Then there is a problem that these regressors are actually generated regressors. So the regressors already have an estimation error because we use estimated psi's, we don't have the true factors. And in addition, this guy is also estimated. So we have different sources of estimation errors, and all these estimation errors have the same convergence rate. So all of them appear in the limiting distribution. So to combine them, we have the usual estimation error type, like this. I call it the white sandwich part. So you have a q to the power of -1 regressor times error structure. And you have an additional term that looks a bit more complicated. But all of these objects, so it's an interplay of this generated regressor problem with the fact that we have also estimated eigenfunctions multiplied on the right side. But it seems complicated, but it's an object that you can nicely handle and also nicely estimate because it has nice moment estimator based sample counterparts. So first, these VT and CT, these are all, these are mean zero, alpha mixing processes. We can apply a pointwise CRT there. What we also assume is differentiable sample curves. That implies that all these curves also have, these objects that appear here are also differentiable, which implies that this entire object here is stochastic equicontinuous. So we have convergence of finite, of the, we have the finite, here the finite dimensional distributions, they are Gaussian, and we have stochastic equicontinuity. So we get a weak Gaussian limit to a process, GRS. It's a Gaussian field, a random Gaussian field, or you may call it a Gaussian surface. It's centered and it has a specific covariance structure. And this covariance structure can be easily estimated consistently. So if you look at pointwise evaluations, you get this nice limiting result from which you can build your inferential methods. So you can build standard errors. This is also under heteroscedasticity, but I assume no autocorrelation. If you want, you can also play around here and incorporate autocorrelation or clustered standard errors or whatever you like. Here we focus on this case, and we get a valid, asymptotically valid confidence set with the right asymptotic coverage probability. All right. Multiple extensions, actually, it's not much more complicated. So we want to regress YT on maybe different scalar variables and, let's say, J functional variables. What we do now is we assume that each functional regressor has such a factor structure with each an individual Kj, each has individual factors, and looking at the pairwise cross-covariance operator of Y with each xjt, we can consistently estimate these psi's. We can consistently estimate, looking at the pairwise of the eigenvalues of this pairwise cross-covariance operator, the number of factors for each regressor. So in total, we get also a finite dimensional regression, which is defined like this. So here we can get the beta hat j's also by estimating these guys. Again, a generated regressor problem. Regress y on these guys. We get coefficient estimates for this guy, from which we can build our beta hat j for each functional regressor j. This is what we want to do in practice. We want to control also for autocorrelation, so add enough lags of the dependent variable and add also further functional variables to get really what we do in econometrics to make really ceteris paribus arguments after adding the right control variables. So Kj is, as I said, the rank. This is basically exactly the same strategy as before. There's a full set of assumptions. So to conclude, we have the error. So again, error and factor term. This was the X star. This is the epsilon. Epsilon is non-predictive. The factors are predictive. That means that this matrix must have full rank. We have the normalization. We have an exogeneity, also a martingale difference sequence assumption. This is a standard identifiability assumption. We need that, of course, that the design matrix must be positive definite. We have a weak dependence assumption and a smoothness assumption that paths are differentiable. And also here we get for each functional regressor a separate Gaussian field in the limit on the on AB squared, from which we can build a nice CRT from which we can do for each functional regressor conditional on the other regressors inference.
Sorry, I probably missed that. So because we don't need any Hug standard errors, we work as you said, so no serial correlation. Where is that in the assumptions that we don't have?
Right. So here let's. So I assume here the error term is given the lagged error terms 0. As I said, you can do everything else also with Hug. So if you only have exogeneity and you can drop this here. And then what happens is that these guys are no martingale difference sequences anymore in the limit. So here what actually appears here then are long run variances. So you have to ensure that you have then you need an estimator for the long run, of the long run variance actually. So that covariance is not so easy because it is not, there's only the contemporaneous effects, and here the infinite sum of the rest then also appears. We try to avoid it here because it's an obvious extension, but makes it makes the notation just heavier. So I would argue in empirical practice, it's anyway often a good idea to incorporate many legs of the dependent variable to capture the time dynamics. But of course, that would actually appear here, and then you have here a long run variance estimator, and then you have to, asymptotics is a bit more involved than to do. All right. Maybe I talk a bit about the application. Maybe I skip the simulations because they often work. So what we have is that coverage rates are nice. If we ignore the generated regressors problem, coverage rates are bad. So it is really important to incorporate that. That is what we find. And also, it works really good. So under standard DGPs, we are often quite close to if we would know the true parameters. So I mean, not the true beta, but all other true parameters that are included, like the true k, the true psi, and the true factors. Also, estimation of k works here. Let's talk about the application where we regress prices on lag prices and information about the demand and the supply side, as I said in the beginning. This setup is actually taken from a different paper where they do exactly this in a big vector autoregressive structure using, so it's very high dimensional because more regressors than observations, and they use just lasso. And we just picked the same model setup. So this is why we chose here 5 legs. It's only work days. This is by 5 legs for each regressor. What we see, so on a discretized level, if we would build at least for the price curve, there are actually only 24 different observations. But we see that the estimated k is often between 4 and 5, which is an indication that our model is actually makes sense. So there seem to be less factors than directions available in the data. So it's actually, if you take the sum of these numbers, this is the number of regressors that appear here, and we control also for other scalar variables. And we get this already the picture I showed you, so we can now do nice ceteris paribus analysis for the lag price, today's price conditional on the demand and supply effect. You can build the confidence interval. So this is the lower, and this is the heat map of the lower, and this for the upper confidence band, and this is the one in the middle. So if you see, for instance, that this is red and this is red, then this is out. Then this the true. So then the 0 is not included. So this is also why you have here significant effects. And you can do that also for the load effect. So for the load effect, if there is high expected demand on the main diagonal for the same hour, we also expect a high price. But there's also an effect that if there is a high demand in certain times, maybe it's better for the price if you consume more in other time periods. So then you can see effects like for instance, this one is negative meaning that if prices apparently are high, or if demand is high, expected demand is high at 17, then the prices at 7 are lower, actually. So you can think about these, you can analyze these effects and also other effects. By the way, the time is already up, right? Or is it?
4 minutes.
4 minutes. Okay, good. Then maybe I conclude already. So we have also an effect of negative effect. Makes sense. The main diagonal. If there is a lot of wind expected for a certain time, then prices are expected to be low. Maybe if there is a lot of wind expected at 17, but no wind expected at 10, it's a bad idea. It has a negative effect on the price at 10. So this also tells you that effects on the price depend also where wind is expected in other time periods of the day. And also confidence bands you can interpret. In R squared, you can build that. Apparently, 7 a.m. prices less cannot be estimated or cannot be predicted that well as the other prices. So it's 0.7565. It's not at 0 here. And in a, let's say, a horse race, to compare it with the lasso, we do not claim that we have a better predictive model. There are machine learning methods often outperform. There is one expert model out there that uses such a actually also such a regression framework, but within a scope that you can estimate with a usual regression model, so that is not high dimensional, that you can still interpret. So this is a good estimator in terms of prediction. There's a good model in terms of interpretability. There is also a naive forecast, let's say from yesterday. And what we see is that we are very close in terms of the predictiveness to the lasso. We are better than this expert model and much better than the naive model. So we offer both interpretability, a statistical inference, and also a good prediction model. And I'm sure that if we tweak it further, it is also possible to improve the predictive power, but that is not the main point of our paper. We have a R package, so we try to do it as close to the LM function as possible. So you can type FLM, and then you need a matrix form, data, price, and other variables. So you can apply that using our R package if you like. And to sum up, our model is, of course, more restrictive than the classical model, but I would say it's still plausible compared to only assuming finite dimensionality, and we get nice asymptotic results from which we can build inferential theory. Also, we exploit specifically the cross-covariance structure to get the directions that actually explain the dependent variable well. Right, I think this is it. Thanks a lot, and questions.